So we're going to consider a quantum field theory in Minkowski spacetime M with a Hilbert space H that contains a vacuum state omega. So there's an algebra of local operators whose action produces all states from the vacuum, or at least all states in what's called a superselection sector. If there are magnetic monopoles, we don't create them with local operators. You can consider this to be more or less the definition of quantum field theory. After all, people started with fields, then they quantized it, and they had an algebra of field operators. And to decide what the Hilbert space had to be, it was something that the operators could act on. So the fact that the local operators can produce all states from the vacuum is basically the definition of quantum field theory. To keep the notation simple, we'll assume the operator algebra is generated by a Hermitian scalar field phi. So states obtained by acting on the vacuum with a series of field operators and arbitrary points in Minkowski space-time are dense in the Hilbert space. The Reeh-Schlieder theorem says that actually you get a dense set of Hilbert space states if you restrict the points to any possibly very small open set. So just restricting to this little open set in M, field operators in U can create a dense set of states. So it's a little surprising at first because it makes all the rest of the field operators seem unnecessary. Now, if this is false, there's a state chi that's orthogonal to whatever you could make by acting on the vacuum with field operators in U. So we're going to show that there's no such chi by showing that any such chi is orthogonal to all such states without the restriction that the x's are in U. So since states created by the phi's are dense, this implies that chi is 0. So assuming that this function vanishes when the x's are in a small open set, we'll prove that it actually vanishes even if the x's aren't restricted in that way. So I simply define a function f of the x's by this definition, a matrix element from the vacuum to some state chi of any product of field operators. We're given this function vanishes if the x's are in a small open set. We want to prove it vanishes for all x's. Well, as a first step, we pick a future pointing time-like vector t, and we consider shifting the last point by a real multiple of t. So xn goes to xn plus u times t. So let g of u be the matrix element with xn shifted by u times t. Well, g of u vanishes if u is small enough, because then xn plus u times t is still in the open set curly u. This should be curly u. Also, if h is the Hamiltonian, we can write g of u this way, where shifting the operator by ut means conjugating by e to the iu times the Hamiltonian. And then, since the Hamiltonian annihilates the vacuum, we can write g of u this way. But because h is non-negative, it follows from this representation that g of u is holomorphic in the upper half u plane. In other words, if we give u an imaginary positive imaginary part, that only is going to make things smaller. So we have a function that's holomorphic in the upper half plane and 0 in part of the real axis. Such a function is actually 0. If we knew it was holomorphic on the real axis and not just above the real axis, and vanished on a segment of the real axis, we'd say that it has a convergent Taylor series expansion around a point in the interval where it vanishes. And this expansion would have to be identically 0. And then we'd say that a function with a 0 Taylor series expansion is 0. We can't quite say that right away because, to begin with, g of u is only holomorphic above the real axis. But we can get around this using the Cauchy integral formula. So here's a point in the upper half plane. And we can write g of u by an integral over this contour using a Cauchy integral formula. But since the function is holomorphic in the upper half plane and continuous down here, we can deform so that part of the contour is on the axis. And we can take that part to be in the interval where the function vanishes. So then we get a Cauchy integral formula where we just integrate over this. And then we can take u through and learn that it's holomorphic even down below, and in particular on the axis. So in this way, we prove that such a function g of u is actually 0. So now we know that as long as the first n minus 1 points are in the small open set u, this function still vanishes if xn, the last point, is shifted by a multiple of the time-like vector u. For example, the time-like vector might just point in the time direction in some Lorentz frame. So we've learned we can shift the time coordinate as we want and still have vanishing. Now we do this again, picking another time-like vector t prime and replacing xn prime by xn double prime, plus, which is now xn prime plus u prime times t prime, where u prime is still real and t prime is a different time-like vector. We go through exactly the same steps and learn that we still have vanishing if xn prime is replaced by such an xn double prime. But any point in Minkowski space can be reached from u by zigzagging backwards and forwards in various time-like directions. So we learn that we actually have vanishing with no restriction at all on xn, as long as the first n minus 1 points are in the small open set. So the next step is to remove the restriction on the next to last point. So we pick t as before, a time-like vector, and now we make a common shift of the last 2 points in the t direction, which means we shift the last 2 points like this. We shift them both by a common multiple of t, by ut, for some real u. And now we look at the corresponding shifted matrix element. And it vanishes for small real u just as before. And also it can be written like this, with an insertion of e to the I UH just as before, but now in a different place, one step to the left. And that implies it's holomorphic in the upper half plane. So it's identically 0 again. So now we repeat the process by shifting the last 2 points in some other time-like direction, and we learn that our matrix element is 0 with no restriction on the last 2 points if the first n minus 2 points are in u. And having gotten this far, we keep going. We next remove the restriction on xn minus 2 by shifting the last 3 points by a common time-like vector. And after shifting them in the t direction, we shift them back in the t prime direction. And then remove the restriction on xn minus 2. And then we do it over again for the last 4 points, and so on. So we end up proving the Reeh-Schlieder theorem. An arbitrary state, more exactly a dense set of states in the vacuum sector, can be created from the vacuum by acting with the product of local operators in any small open set U in M. Yes?
So, this holomorphicity
yes.
with respect to U that entered everywhere?
Yes.
So is there some assumption on the spectrum or something?
We use the fact that the Hamiltonian is bounded below by 0. Well, actually, bounded below would have been good enough, but it's actually bounded below by 0. We use the fact that the operator e to the I UH, as an operator actually, is holomorphic in the upper half U plane, simply because when U has a positive imaginary part, since the energies are positive, that gives an exponentially damped factor. So what we used, we did not use Lorentz invariance directly. We used the fact that the energy momentum in any light-like direction is bounded below by 0. Bounded below would have been good enough, but it's bounded below by 0. So we use the fact that the Hamiltonian is bounded below by 0, but also the Hamiltonian plus epsilon times the momentum is bounded below by 0 if epsilon is not too big. We use that fact, second fact, when we shifted in a different time-like direction. So we had not just one direction where we could make this argument, but the argument was good in any time-like direction, because the Hamiltonian plus any sufficiently small linear combination of the momenta is still bounded below by 0. We only needed bounded below, but it's bounded below by 0. So that makes this matrix element holomorphic in U in the upper half plane. And holomorphy in the upper half plane, together with vanishing on part of the real axis, is what we used at every step in this argument. And this little Cauchy integral, sorry, where is it? This little argument with the Cauchy integral theorem, Cauchy integral formula, shows that that's enough to prove vanishing of the function.
Is this also kind of a proof of the edge of the wedge theorem?
Well, no. We used what you could call the one-dimensional edge of the wedge theorem. But in one dimension, it's more elementary, which is why I gave the proof here from the Cauchy integral formula. The multi-dimensional edge of the wedge theorem is a more sophisticated theorem, which is important, but which we won't use in today's lecture, so I will not explain it. You'll find references where the Reeh-Schlieder theorem is proved invoking the multi-dimensional edge of the wedge theorem, which makes it sound less elementary than it is. So I made a point of presenting the proof using only the one-dimensional version of the theorem, which is elementary. The alternative would have been either to invoke a theorem whose proof you didn't know, or else to give what would have been a rather technical-looking proof of the edge of the wedge theorem. I may have gone too fast to be understandable, but I really only used the Cauchy integral formula in an elementary way. Sorry, I didn't repeat the questions like I was supposed to, but maybe I indicated the questions in answering. So one question had been whether we proved the edge of the wedge theorem. No, we avoided using it.
Is there some restriction? I mean, is this set U supposed to be on a spacelike surface?
U? No, the curly U is an open set in space-time, so it's not on a space-like surface. It's a space-time open set.
And there's no size restriction, it can be as small as...
You just saw the proof. I hope you found it convincing. Sorry, the question was whether U can be as small as you want. Yes, it's as small as you want, but it's an open set.
And nothing matters when you cross the light cone of other operators?
Nothing
matters when you cross light cones of other operators?
Well, the statement didn't involve other operators. The statement was that operators in the set U, acting on the vacuum, create a dense set of states in Hilbert space. They can cross each other's light cones.
Because the correlation of states off pretty dependent, that has a pole, and you have like level separators.
There wasn't any unstated restriction. So the question was whether singularities when two operators cross the light cone cause a trouble. Evidently not, because they did cross each other's light cones at some point in this proof. I can't hear all that, sorry.
Oh, sorry.
Speak up.
Oh, I agree that like you don't want it to matter for
Yes.
argument.
Yes.
But I was just curious if I wrote like just a bunch of like free fields and I had some like power follow-ups with the like xi differences squared. I would imagine that somehow crossing light cone would give like that whole correlation would have some funny pole in it. But I'm not saying.
Well, careful arguments like Streeter and Witten consider some slightly smeared versions of these correlation functions. And then they give, well, they almost give exactly the same proof I said, except they use the edge of the wedge theorem, which I avoided using.
So is the intuition behind this that wave packets can spread reasonably fast?
Is what? Sorry?
The wave packets can spread arbitrarily fast.
Rather than answering directly, let me postpone that question, and I'll state what I think is the intuition. Then you can ask another question if you wish. Where were we? Okay, now we want to discuss the interpretation of this theorem. So first of all, does it contradict causality? So at first sight, it seems unintuitive. Consider a state of the universe that on some initial time slice looks like the vacuum near you, but it contains the planet Jupiter in some distant region, space-like separated from you. So let J be a Jupiter operator whose expectation value in a state that contains the planet Jupiter in region V is close to 1, but its expectation value is close to 0 if there's no planet Jupiter in region V. So the Reeh-Schlieder theorem says there's an operator X in region V. This should be a operator X in region U, such that the state x omega contains the planet Jupiter in region V. As written, the statement isn't unintuitive. But The corrected version, where V is replaced by U, is a little unintuitive. So the surprising thing is that an operator in region U can create the planet Jupiter in region V. So that means the vacuum expectation value of the Jupiter operator is 0, because in the vacuum, there's no planet Jupiter in region V with high probability. But if you act on the vacuum with some operator x in region U, then in that state, the Jupiter operator has a large expectation value, close to 1, because there's almost definitely a Jupiter planet in region V after acting with operator x in region U. Is this a contradiction? Well, first of all, this matrix element can be written this way, where I replace x by its adjoint. And then since J lives in region V and x lives in region U, they commute with each other. X dagger and J commute. So 1, which is this, can also be written like this. The vacuum expectation value of omega times J x dagger x is close to 1. If x were unitary, there would be a contradiction between these two claims, because if x is unitary, then x dagger x is 1. But the Reeh-Schlieder theorem does not tell us we can pick x to be unitary. It just tells us there's some x in region U that will create the planet Jupiter in a distant region V. Comparing these formulas, all we find is that in vacuum, the operators J and x dagger x have a non-zero correlation function in the vacuum at space-like separation. But this shouldn't surprise us because, for example, in free field theory, a free field has a non-zero correlation function at space-like separation. So space-like correlators in quantum field theory happen all the time. So there's no contradiction with causality as there would have been if the theorem claimed that x could be assumed to be unitary. Rather, the intuitive interpretation of the Reeh-Schlieder theorem involves entanglement between the degrees of freedom inside U and those outside U. So to explain our intuitive picture, let's imagine, as Matt Hedrick did this morning somewhat heuristically, that the Hilbert space of our quantum field theory has a factorization as a Hilbert space of degrees of freedom inside U times 1 of degrees of freedom outside U. That's not exactly true, but let's imagine it was. Then, as we said this morning, any state in the vacuum, in the Hilbert space, such as the vacuum, would have a Schmidt decomposition, where we can assume the psi u's and the psi u primes to be orthonormal. We also assume the p's are positive, where we would drop some terms from the sum. In general, when we write the vacuum state this way, the psi u's and the psi u primes are not bases, because there might not be enough of them. But something like the Reeh-Schlieder theorem will be true whenever the psi u's and the psi u prime are bases. Let me just show you that quickly. So, since the psi u primes are a basis, any state capital psi could be expanded as a sum of psi u primes tensored with something in HU. Now, to imitate the Reeh-Schlieder theorem, I want an operator x that acts only on HU, not on HU prime, that'll turn omega into psi. And that's no sooner said than done. Since the psi's are a basis and the p's are non-zero, you can define an operator x acting on HU by saying that it maps the square root of p times psi iu to lambda I. So we found an operator x acting only on degrees of freedom in U, such that x omega is psi. So in other words, we've shown that in general, in quantum mechanics, whenever you have a state, well, such that the coefficients in the Schmidt decomposition form bases, which is equivalent to saying that the reduced matrix element of either factor is invertible. Whenever that's the case, you have an analog of the Reeh-Schlieder theorem, where every state in Hilbert space can be obtained acting on this given state by an operator that only acts on HU and not on HU prime. And you simply find this operator by hand by comparing the two Schmidt decompositions and asking how you can act on the first factor to turn this into this. You simply want an operator x that maps this vector to this one. Yes?
Does the Reeh-Schlieder theorem imply the converse, that there is a full rank Schmidt decomposition?
I think we'll find a yes answer to that question in a second, so let me postpone it. So a state where the p's are all positive and the psi and psi u prime are bases might be called a fully entangled state. It's not really standard terminology, and the reason is that for most applications, it's not useful because it's not interesting to distinguish whether one of the p's is 0 or 10 to the minus 100. But for the kind of considerations in today's lecture, it is useful to speak of a fully entangled state where the analog of the Reeh-Schlieder theorem applies. Instead, a state is called maximally entangled if the p's are all equal, but this is not possible for Hilbert spaces of infinite dimension, as in quantum field theory. So the Reeh-Schlieder theorem means intuitively that the vacuum state omega of a quantum field theory is fully entangled in this sense between the inside and outside of an arbitrary open set U. But I want to stress that the decomposition we started with is certainly not literally valid in quantum field theory. If it were, then in the Hilbert space there would be unentangled pure states psi tensor chi with psi in the first factor and chi in the second. But that's not the situation in quantum field theory. In quantum field theory, there is a universal ultraviolet divergence in the entanglement entropy that was described in Hedrick's lecture this morning. The entanglement entropy of in the vacuum between degrees of freedom in U and those outside U is ultraviolet divergence. And the leading ultraviolet divergence is universal. That is, it's the same for any state. The leading divergence is universal because any state looks like the vacuum at short distances. Now we're going to discuss a corollary of the Reeh-Schlieder theorem. So now we consider two space-like separated open sets in space-time, curly U and curly V. Let B be an operator supported in V. Suppose it annihilates the vacuum. Well, if A is supported in U, then A and B commute because they're space-like separated. So B of A omega would be A of B omega, but that's 0 because B omega is 0. So if B annihilates the vacuum, it annihilates all states of the form A omega. But the states A omega are dense in H according to Reeh-Schlieder, so B identically vanishes. Thus, if B is supported in an open set V that's space-like separated from U, small enough so that it's space-like separated from U, then B on omega can't be 0. If B and omega was 0, we'd prove using Reeh-Schlieder that B is 0. The roles of U and V are symmetrical, so also for any A non-zero supported in U, A on the vacuum isn't 0. So that's the corollary of Reeh-Schlieder. First, it says that that you can make a dense set of states by acting on the vacuum with operators in a small open set U, and the corollary says that such an operator can't annihilate the vacuum. Now let A sub U be the algebra of operators in region U. We've proved two facts about how this algebra acts in the vacuum sector. Well, one is the Reeh-Schlieder theorem that states A omega are dense in H. The jargon is that omega is what's called a cyclic vector for the algebra A sub U. This is the definition of that statement. Second is the corollary that if A is non-zero in this algebra, then A does not annihilate the vacuum. That's described by saying that omega is a separating vector for A sub U. So in short, the Reeh-Schlieder theorem and its corollary say that the vacuum is a cyclic separating vector for the algebra of operators in any small open set U. So I want to go back to the case of a quantum system with a tensor product Hilbert space just to give intuition about what cyclic separating means. So let A be the algebra of operators on the first factor. So if the quantum field theory Hilbert space did factorize as a Hilbert space inside times a Hilbert space outside, then the operators on the first factor would just be the operators in region U. But in finite dimensional quantum mechanics, we can just let A be the operators on H1. Now, a general vector with its Schmidt decomposition of this form is cyclic for A if the psi 2's are a basis for H2, and it's separating if the psi 1 are a basis. So this assertion is very similar to things I already said. But you see, if you take an operator that only acts on the first factor, to annihilate psi, it would have to annihilate each of these. But because they form a basis, that operator would actually have to annihilate all of H1. In other words, it would be 0. And that's the separating property. And the cyclic property I essentially explained a few moments ago when I explained that the analog of Reeh-Schlieder holds in this situation if psi 1 and psi 2 are bases. So in short, the Reeh-Schlieder theorem and its corollary corresponds in ordinary quantum mechanics to a situation where the vectors in the Schmidt decomposition form bases of the respective states, or equivalently, where the density matrix of either factor is invertible. I think by now I answered one or two questions that I postponed. But anyway, I can stop here for more questions. Yes?
So what if the Hilbert space was written as H1 tensor H2 tensor H3 or more factors, and we were interested in generalizing these statements to conditions for this state being cyclic with respect to the algebra just acting on H1?
That makes perfect sense because I didn't say anything. The question is, could H2 be a tensor product of two other spaces? So in everything I've said, then yes. Any other questions? Yes?
Can you illuminate the terms cyclic and separating, where they came from?
Well, they're jargon used by people in operator algebras, which is a subject I don't know well. But separating is semi-intuitive. An operator maps the vacuum to some other state. I mean, if it always does that, it's separating. But I cannot give a good answer. The question was where the term cyclic and separating come from, and I have to plead ignorance, I'm afraid.